Welcome to Scale Up University. Welcome to the course on designing data intensive applications. So, this is the lecture number 6 of module 1. And in this lecture, we will be discussing hardware faults in practice. So, if we talk about the lecture overview, like what will be there in this lecture. So, hardware faults in practice. So, see, the idea is that in large scale systems, hardware failure is not an exception. Rather, it is a background process. So see, like if we talk about small scale, at small scale, we have like one server, and when we are dealing with just one server, it feels very stable. You feel like, oh, it's very stable. But when you scale the system and introduce thousands of servers, then what will happen? We'll have thousands of disks, thousands of memory modules, hundreds of switches, and multiple data centers. So at scale, you will see that something is always breaking. So statistically, you can say that something is always breaking. And hence we say that hardware failure is a background process. In large scale systems, hardware failure is not an exception, rather it's a background process. Why? Because at scale, statistically, it has been seen that something is always breaking. And that is what this lecture is about. So this lecture explores how hardware failure occurs, like how hardware fails, what those failures look like, why redundancy is the only long-term strategy to handle hardware failures, and how to reason about reliability mathematically. Like if we want to deal with reliability mathematically, then we have something called as MTTF, and what it is, we will discuss that in detail in this lecture itself. So if we look at the topics that we will be covering in this lecture, so we will talk about disk failures, memory corruption, network partitions, power outages, why hardware redundancy matters, mean time to failure, that is MTTF intuition, and the big architectural lesson we will learn from this lecture itself. So all these topics we will cover in this lecture one by one. So this is the module 1, trade-offs in data systems architecture, lecture 6, hardware faults in practice. And we are starting with the first topic of this lecture, disk failures. So if we talk about like why disk fails, so in hard disk drives, we have moving parts, because hard disk drives, if you look at it, there is a magnetic disk which keep on rotating. So hard disk drives, it is mechanical in nature, wherein it has got moving parts, magnetic surfaces, which wear over time. The moving parts and magnetic surfaces, they wear over time, and hence hard disk drives, it has got a lifetime. Like after a period of time, it might degrade and it might fail. Even in SSDs, that is solid state devices, it fails because of limited write cycles, firmware bugs, fail under high load. So because of all these factors, even solid state drives, because solid state drives, they are not mechanical in nature, they are electronic in nature, and despite of that, they also get failed because of some firmware bugs under high load, like they have limited write cycles, and because of all these factors, even SSDs they fail. If we talk about common disk failure modes, so we can have complete disk crash, sector corruption, gradual performance degradation, there's a gradual performance degradation, silent data corruption, and write failures. So common disk failure modes, if we talk about complete disk crash, sector corruption, gradual performance degradation, silent data corruption, and write failures. Now there is one very dangerous case. So these are like some different common disk failure modes, and the dangerous among all of it is the silent data corruption. Because just imagine if the data silently gets corrupted, it can be very dangerous. Because i- if the failure is visible failure, it's okay because we got to know that okay, something failed. Since we are aware of that failure, we can like come up with a solution, or we can try to at least handle that failure. But silent corruption is like silent data corruption is like invisible failure, and since we are not at all aware about the failure, the impact of the failure, it will spread, and it might also replicate. So disk returns incorrect data. So if the disk corrects returns incorrect data, then it's not like a because we are unaware of it. So corruption spread. So disk returns incorrect data, no error reported, and corruption will spread to even replicas. Because see, we already saw, and in this lecture we will see that to handle the hardware failure, we use the concept of redundancy, wherein we will keep the backup. We call it replica also. So here in this diagram, these replicas you are seeing, they are the backup disk. So whatever the main disk is containing, exactly same information the backup disk is also containing. Now, if silently data gets corrupted, so that corrupted data, it will be transferred to replica also, because we are unaware about that data corruption. So it's a invisible failure. So silent failure, invisible failure is very dangerous, because the incorrect data, now it gets to the replicas also. Now what are the ways systems protect against disk failures? So one of the like very common and very important way is the replication, which we already saw. In replication, we just maintain the backup. Then we also have something called as RAID, which is like redundant array of independent disk. Redundant array of independent disk. We also have mechanisms of checksums. So checksums can help us in checking for silent data corruption, scrubbing, periodic scrubbing, write ahead logging. So these are like some of the ways through which systems protect against disk failures. Now here write ahead logging means whenever we are trying to write anything on the disk, we are making a log of it. Now the advantage is that, see, many a times what might happen is that, let us suppose you have to write a complete paragraph, but after two sentences the system got turned off, shut down, or something happened. Because of that, we were not able to write it completely. So what write ahead logging, what it enables is that before writing, a log was maintained, wherein we have exactly, like we know how much content was written on the disk. And with this log information, we can very easily see that, like, incomplete writing before system shutdown, abrupt shutdown. Then when the system restarts, because of using this write ahead logging, we can start from where we stopped. So this is like a very powerful mechanism. Here we like data inconsistency. We are protecting the disk from data inconsistency. From checksums, we can identify silent data corruption. Scrubbing is also like a similar mechanism, wherein like periodically we can just keep on checking for the data. So the idea is very clear. We can like the systems protect against disk failures. Systems can protect against disk failures. Now, one very important key takeaway from this slide: never trust a single disk. So the idea is that always we should have replication in place. We should never trust a single disk. Memory corruption. Now see, memory, it's the RAM. It's volatile in nature. It's very fast, but it's volatile in nature. Now, why memory corruption happens? It might happen because of electrical noise, cosmic radiation. In cosmic radiation, like some high frequency waves, it might flip the bits. It can make 0 as 1, 1 as 0. That we call it bit flips. Memory corruption might happen because of manufacturing defect, overheating, or firmware bugs. So these are like some of the common reasons for memory corruption: electrical noise, cosmic radiation, manufacturing defects, overheating, and firmware bugs. Now let us suppose a single bit flip happened. Now this is very dangerous. It can flip the bits, and because of the bit flip, it can even change the number. So it can make 10 as 12. It can corrupt a pointer, wherein the pointer might now point to a different address. It can crash a process, and it can corrupt cached data. So a single bit flip can be very dangerous. Now, if we talk about types of memory errors, so we can have transient bit flips, which are temporary in nature. We can have persistent memory cell failure. So see, bit flip is temporary in nature because it can be undone. Like let us suppose some bit flip happened, we can overwrite the content, we can overwrite the data, then we can reverse. So that's why transient bit flips, it is temporary in nature. But cell failure is something which is related to the hardware and it is permanent in nature. So persistent memory cell failure. In that scenario, we have to change the memory itself, the hardware itself. And we can even have buffer overflows. So they are software triggered. Buffer overflows means we are trying to add more data than the capacity of the memory. Now, what are the mitigation strategies to avoid memory corruption? So we can go for ECC, that is error correcting code memory, process isolation, data validation, checksums, crash recovery mechanisms. So these are the mitigation strategies to deal with memory corruption. Now the key insight which we should take away is memory is fast but unreliable. So this is like a very important insight. See, we make use of memory because it's very fast as compared to hard disk. But very important observation, memory is unreliable because this bit flip, manufacturing defect, overheating, firmware bugs, overflow, these are like common scenarios. So memory is fast but unreliable. That we have to keep in mind as system designers. We have to keep this in mind. Network partitions. Now first let us understand what is a network partition. So when some nodes cannot communicate with others, even though nodes are running. So network partition means like I have a network of many nodes. I have a network of many nodes. Now these nodes, they all are running, but they are not able to communicate with each other. Like. So here we can see a partition wherein they are not able to communicate with each other. So this is, we call it like the network partition. So network, all the nodes are running, but because few nodes are not able to communicate with each other, there is a break, there is a partition in the network. So network partition, it creates split brain scenarios, an inconsistent view of the system. Now very important question in front of us, why network fails? So network fails because of switch failures, router misconfiguration, cable damage, congestion, or cloud provider incidents. So these are some of the reasons for network failure. So network fails, why networks fail? Switch failures, router misconfiguration, cable damage, congestion, cloud provider incidents. Now, next very important question. Why network failures are so dangerous? See, network failures are dangerous because we it creates a confusion. Like we are always in a state of confusion in deciding whether the node is dead, issue is in the node, or the network is slow, or is the network broken, because we are puzzled. See, the idea is that now, see, because of the network failure, packets we are not able to exchange. So now a node is waiting for an incoming packet and it is not receiving it. Now that node might get puzzled. It might like or we might get puzzled that why this node is not receiving the packet. So we might think the node, whether the other node is dead, that's why it is not able to send the packet, or we might think the network might be slow, or we might think is the network broken. So there is a confusion is there. So that's why distributed systems, they must decide whether we should keep on waiting. See, we cannot keep on waiting forever, because if the network is broken, there is no chance that the packet we will receive. So how much to wait is a decision criteria we have to fix, and we should keep on retrying, but to a certain extent. And how to decide failover, like what's the point, or how to decide whether like the network is broken. So here we have to have some mechanism in place. So this is where deep trade-offs emerge, like how much to wait, how long we should keep on retrying, and when to decide that okay, there is a network failover, network partition. And hence it's a challenging problem to deal with, network partition. We are discussing hardware faults in practice, and we are discussing different kinds of scenarios that we might see: disk failure, memory corruption, network partitions, power outages. So power outages is also a kind of a hardware failure, hardware fault. Now see, power failure, it's very clear to us that now what are the different modes. We can have full data center blackout, we can have partial rack power loss, we can have UPS, that is the uninterruptible power supplies failure, and we can have generator malfunction. So these are like different power failure modes. If we talk about the impact of power outage, so we will be seeing sudden shutdown, incomplete writes, corrupted logs, because abrupt like sudden shutdown will lead to corrupt logs, incomplete writes, restart storms. And what are the protection mechanism, how we can protect the system from power outages? So definitely we should have UPS, that is the uninterruptible power supplies in place, backup generators, multi-region replication. Multi-region replication is very important, so that if in a region power failure occurs, we can use the replica of other region, so that the show must go on. Write ahead logging, crash safe storage engines. These are the protection mechanisms in place to deal with power outages. So the key takeaway for us is power failures are abrupt and brutal. So systems must be crash safe by design. So this is like a very important discussion point. Why hardware redundancy matters. Now see, very important point we are discussing. One of the golden strategy to handle hardware failure or hardware fault in practice is hardware redundancy. So hardware redundancy is the foundation of reliable systems. So see, the idea is that individual machines are unreliable, because we already saw disk might break, memory might corrupt, there might be power outages, network failures. So individual machines are unreliable, and we need reliable systems. And we can get reliability from replication, diversity, and isolation. So replication means redundancy. Diversity means using different, like if we are using disk, we should use disk of different manufacturers. Isolation means system should be modular, like they should be isolated, like every component of a system should be responsible in accomplishing a certain task. They should not be tightly coupled. So if we talk about redundancy types, because now it's very clear that we can achieve reliability via redundancy. So types of redundancy we have: data replication. In data replication, multiple copies of data is maintained. We have service replication, multiple instances of application are running. We have geographic redundancy, wherein we are creating the replicas in multiple regions. And we have network redundancy, wherein we are establishing connections between nodes via multiple paths. Whereas, wherein if one path gets break, we can utilize the other path. So we can achieve redundancy in four ways: data replication, that is the multiple copies of the data; service replication, multiple instances of the application; geographic redundancy, multiple regions; network redundancy, multiple paths. Now, if we talk about important trade-offs, see, redundancy is always about trade-off, wherein redundancy, it improves reliability and availability. Because with redundancy, system will become reliable, because if one node gets corrupted or if it is down, we can use the replica node as the backup. So reliability and availability is improves, but redundancy also increases the cost, complexity, and consistency challenges. So there is always a trade-off is there. So redundancy, it introduces coordination problems. So redundancy comes with a cost, like price, like the price will increase, complexity cost is there, and consistency challenges, coordination problem is there. Mean time to failure intuition. Now, what is MTTF? The full form of MTTF is mean time to failure. And what it means, it's like a mathematical measure of reliability. It means the average time a component operates before failing. So the average time a component operates before failing is the MTTF, mean time to failure. If we talk about an example, if we take an example, if a disk have a MTTF of 5 years, it means a disk operated for 5 years on an average before failing. Now, now MTTF, it is like a average, it's like a mathematical measure. Now, it does not mean, like very important observation, MTTF of 5 years, it does not mean that disk will last for 5 years. So if the MTTF of disk is 5 years, it does not mean that the disk will last for 5 years. The disk might uh, break down in 2 years itself, in 3 years itself. So MTTF is a statistical measure. It is giving us an idea about the average time a component operates before failing. It is not about how long the component will last. So this difference is very important. Now MTTF for individual components, it is different, and at scale it changes. So why MTTF changes at scale? So see, if we talk about one disk, so if one disk fails every 5 years, so if the MTTF of one disk is 5 years, then if we take 1000 disks, then 1000 disks, we can expect a failure every few days. So this is a very harsh reality, and it might be very surprising to you that, let us suppose I have a disk with MTTF of 5 years, and if I'm using thousands of those disks, now those disks with MTTF of 5 years, we are seeing them to fail every few days. And that is what happens when we scale the system. So it's a reality that When we scale the system, it multiplies failure frequency. So if we talk about, so then we should consider system level MTTF, because no point of talking about a MTTF of single component, because with scale, failure frequency multiplies. So it's good to talk about system level MTTF. So if your system, it is equipped with thousands of components, then the system level MTTF is much lower than the individual component MTTF. So therefore, large systems are always in a state of repair. And the key insight we should take away from us is reliability is not about preventing failures, because now it's very, very clear to us that in the system level, failures is something which is a normal. Large systems are always in a state of repair. Scale multiplies failure frequency. So reliability is not about preventing failures. We cannot prevent failures. Rather, it's about tolerating failure. It's about detecting failure quickly, recovering automatically, and maintaining invariants. So that's the idea. So the big architectural lesson. So if we talk about the hardware, we from this lecture now we are convinced that hardwares, they fail randomly, hardware fails unpredictably, and hardware fails frequently at scale. We cannot make hardware perfect. Rather, we can design systems that can tolerate hardware faults. So system design is all about designing systems that can tolerate hardware faults. And this is the foundation of distributed databases, cloud infrastructure, and high availability systems. So if you are designing, or if you are dealing with distributed databases, if you are designing cloud infrastructure, if you are designing high availability systems, then this very important thing you should keep in mind, that you should design systems that can tolerate hardware faults and not prevent hardware faults. We cannot avoid or prevent hardware faults when we are dealing with systems at scale. So that's a very big architectural lesson we should take away with us from this lecture. So finally, we completed this lecture. So in this lecture, we saw disk failures are inevitable, memory corruption is real. We also looked into the network partition, wherein networks may also break down, network network failures, power outages also we saw, which is a harsh reality. And we also saw MTTF, it shrinks at scale. And the very important observation, redundancy is mandatory, not optional. So now a very important mindset shift you should have: hardware is unreliable. So reliability must emerge not from perfect hardware. Hardware will fail. So reliability must emerge from architecture, from the system design, from the architecture. So I hope you got a very good understanding of the concepts that we discussed in this lecture. So do subscribe to our YouTube channel, Scale Up University, for more such interesting courses and lectures. Thanks for watching. Thanks for your time.